or the totality of the area in both tails must be 0.01, which means that the area over here must be 0.01 divided by 2, which is 0.005 must be in this tail, which means that 0.005 of the area must be in this left-hand tail. So the question now that we have is, what are these critical values? What are these values here, this critical value here and here, that have that amount of area to the right-hand side of it and have that amount of area to the left-hand side of it? So let's just try to figure this out. Okay. Now, our t-tables provide us with cumulative areas, okay? Actually, no, not cumulative areas. Our t-tables provide us with the amount of area that we're putting in the right-hand tails, okay? Now, in this particular case here, we're putting 0.005 in the right-hand tail. So what we'll do is, we'll go to our t-tables. So we're going to go to our t-tables, our t-distribution tables, okay? The t-distribution itself is t-distribution, okay, is parameterized by degrees of freedom. Okay, our degrees of freedom are listed down this column here. Okay, and the degrees of freedom are defined to be equal to, in a single sample case, is equal to the sample size minus 1. In our situation here, our degrees of freedom is equal to 22. That's our sample size minus 1, so our degrees of freedom are equal to 21. So we're going to come down this column here to 21. There are degrees of freedom. And the amount of area that we have in our right-hand tail is 0.005. So the area, or the probability in the right-hand tail, is 0.005. It's a two-tailed test. Now, we've provided students with tables that allow them to calculate these particular critical values, okay, with respect to the t-distribution. And you can actually see here that, well, we've got 21 degrees of freedom. Our tables here, the degrees of freedom are listed down the first column. Across the first row, we have the amount of area that we're putting in the right-hand tails. So actually what we want to do is we want to go down to the row that has degrees of freedom 21, which is here. And the amount of area that we have in the right-hand tail is 0.005. So actually the critical value that we're interested in is this critical value here, which is on the row 221. Okay, so it's 2.831. So actually when we triangulate in here from 21 degrees of freedom and 0.05 of the area to in the right-hand tail, the critical value is, let me just look that up again, it's 2.831. So this value here is 2.831. Okay? In other words, this value here, okay, this critical value here is 2.831. True symmetry, that means the one on this side is minus 2.831. Okay? Now, hopefully what we can actually observe here is that our test statistic that we calculated, okay, is 2.44. Okay? So when it comes to our decision, okay, let me maybe redo this curve out here again. Okay? So what we have is this. We have our curve centered on 0. The critical value here is 2.831. The critical value over here is minus 2.831. Okay, there are rejection regions. Okay, okay, that's how far we need our test statistics to be away. Okay, but our test statistic, as I said, is 2.44. Now 2.44 is in here. Okay, so this is our t is equal to 2.44. So you can actually see it's not far enough away. It's not greater than this demarcation point here. Okay, so the evidence that we've observed isn't far enough away. This evidence isn't far enough away from 35 to be statistically significant. Okay, so our decision, step 5, our decision, okay, is because it's a two-tailed test, we can actually throw away our signs of our critical values, okay, and also throw away the sign of our test statistic. So our decision is this: is clearly the absolute value of our t statistic is less than, okay, actually maybe the way I should say this is clearly the absolute value of our test statistic is not bigger than the absolute value of our critical value. And what I mean by that is 2.44 is not bigger than 2.831, and as such we fail to reject H0 at the 5%. Sorry, this is actually done at the 1%. Okay, so at the 1% level of significance. Okay, level of significance. So we couldn't reject. We failed to reject. We're still in this null position here. We failed to reject. We've failed to reject this particular null hypothesis. So really what we're saying is that there's no evidence to suggest that the actual population mean, okay, there's no evidence to suggest that the actual population mean, which is the amount of money that students spend on mobile phones per month, that the actual population mean is different to 35 euros. Okay, because our test statistic was not inside our critical regions. Okay, now this is different to say, we're not saying that the actual population mean is 35, we're just saying that there's no evidence to suggest that it's not equal to 35 euros. Okay guys, once again this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this particular video was in some way intuitive, and more importantly I hope that was helpful for you, and thank you for watching. Okay, bye bye.